The biggest ships in the world weigh many hundreds of thousands of tons, yet they still float. It does seem counterintuitive to a lot of people. So just what is it that stops these enormous ships from sinking? For the answer, we actually look to ancient Greece, to a chap called Archimedes. Now, Archimedes was a brilliant mathematician, and he wrote many works documenting his discoveries. For us, we're interested in the work called On Floating Bodies, which he wrote as 2 volumes around 250 BC. Within these volumes is the principle that has become known as the Archimedes principle. Any body wholly or partially immersed in a fluid experiences an upward force equal to the weight of the fluid displaced. Now this applies to everything in a fluid. Take this brick as an example. If we lower it into the water, it's going to sink. But Archimedes' principle still applies. The brick is still experiencing an upward force equal to the fluid that is displaced. It's just the upward force is not enough to counter the weight of the brick. You can measure the amount of fluid displaced by either calculating the volume of the brick mathematically, or measuring the amount of water that has been pushed aside. Measuring this brick gives 20 centimetres, 10 centimetres, and 5 centimetres. The volume is just these 3 multiplied together, and doing that in metres gives us 0.001 metres cubed. This is the volume of the fluid that's been displaced. Looking back at Archimedes, you notice that we need the weight and not the volume. To turn volume into weight, you need to know the density of the fluid. Fresh water is easy to remember. It's got a density of 1,000 kilos per cubic metre, and this is why I wanted the volume in cubic metres. We can find the weight of the fluid displaced by multiplying the density by the volume, which gives us 1 kilo. The brick has displaced 1 kilo of water, and Archimedes tells us that the upward force experienced by the brick is the same as the weight of the fluid, so the brick is experiencing an upward force of 1 kilo. Given that the brick itself weighs 2 kilos, that upward force is not enough to overcome the weight, and the brick sinks. To make an object float, we can turn to Archimedes again, and another one of his principles, which is the principle of flotation. Any floating object displaces its own weight of fluid. Again, we can apply this to the brick. To make the brick float, it needs to displace its own weight of fluid, and there are 2 ways to do that. You can either make the brick lighter, but keep it the same volume, maybe by hollowing it out, or you can keep the brick the same weight and make it displace more water. This is the same as tying a balloon to it, if we assume the balloon doesn't weigh anything. And ships use these exact same principles. They just need to displace enough water that it counters their own weight. Take this ship as an example. Its rough dimensions are 300 metres in length, 40 metre beam, and 15 metres draft. If it was a perfect block, it would have a volume of 180,000 cubic metres. As this is just an example, let's say it's floating in fresh water. It's displaced 180,000 tonnes of water. Because of Archimedes, we know that it's floating because the ship itself, plus the weight of all the cargo, equals 180,000 tonnes. It is the volume of water displaced by the hull that is allowing it to float. You can add more weight. Shippers always want to do this as it allows them to carry ever more cargo. As you add more weight, however, the ship needs to displace more water to remain afloat. And ships can do this quite easily just by sitting lower in the water. They're increasing their draft. Of course, if you add too much weight, the ship will sit even lower still until non-watertight areas become submerged, at which point water will flow into the hull and the ship will sink. Real ships have markings on the side of the hull telling the crew how low it can safely sit in the water. These are known as the plimsoll line, and when the ship is sitting on this mark, it's displacing the maximum amount of water that it's allowed to, so it's carrying the maximum amount of cargo that it can. As ships get ever larger, they simply need to displace more water to remain afloat. Bigger hulls naturally displace more water. The biggest ships in the world float just as happily as small boats. Their bigger hulls displace more water, which generates a larger buoyancy force, which supports their larger weight. It may be counterintuitive, but when you dig into it, it does make sense.